Well, hello and welcome to another DevNation. We're super excited today. I'm excited because we're going to have a lot of fun talking to Bilgin. He's going to walk us through some really fun stuff. You might know him as a guy who's authored the book on things like Kubernetes patterns, and he's going to be doing some really amazing things by talking to us about how to use Kubernetes in very interesting ways today. We're going to have a lot of fun. I recognize in Europe there's some holidays going on, so did I see DJ Maddie on the chat? Please do throw your questions in the chat, though. Let me know if you can't hear, you can't see, and we'll try to sort that out if we can. But throw your questions in the chat, and I'll relay those to Bilgin towards the end of the session. But at this point, what I'd like to do now is turn over to Bilgin and get out of his way, because he's got so much great stuff to talk about. Over to you, Bilgin.
Yeah, thanks, Fleur. And hello, everybody. My name is Bilgin Ibryam, and I'm here today to tell you how I see distributed systems evolving on Kubernetes. This will be a fast-paced talk where we'll not have time to dig into every tech deeper, but we'll just have a quick overview, and we'll try to predict how that may affect probably the future of this technology we are using. Let me proceed. I am working as a PM for Red Hat, and I have been consultant and architect for many years using projects such as Apache Camel. I've contributed to Apache Camel, I've wrote a book about it. And similarly, in the last couple of years, I've used Kubernetes and wrote a book about it. And I kind of have some opinion on how integration might be changing on top of Kubernetes. So I want to start with the question, what comes after microservices? That's a question I'm getting from time to time, and probably you already have an answer, and I have one too. And by the end of this talk, we'll find out what is that. Let's get started with setting up a framework that we will use to evaluate various technologies. Let's say we want to write a service, some business logic that is part of a bigger distributed application. So what are the needs, what are the capabilities we expect from a platform, from different libraries to write such a service? I would say at the foundation, at the very basic, what we need is certain capabilities around lifecycle management. And what I have in mind here is things such as being able to do deployments and rollbacks, be able to schedule and place workloads to different nodes, configuration management, good resource and failure isolation, ability to scale workloads. And these workloads can be of different nature. They can be stateless applications, stateful application, even with serverless characteristics. All distributed applications need network connectivity, but I would say a modern distributed application needs to really master networking. And on the networking capabilities, I have here in mind things such as service discovery and failover, ability to do dynamic traffic shiftings to enable you to do different release strategies, be able to do resilient networking through retries and circuit breaking, and enhance security and observability. These are all the needs I would say are under the networking category. The next one is around resource binding. The components of a distributed applications typically have to talk to each other, and not only that, they also have to integrate with external legacy system and modern applications. And to do that, you need different connectors, be able to talk different protocols, transform different data formats, and even more than that, be able to interact through polling or through event-driven mechanisms. And all of that I would categorize as binding needs. And at the last category, but possibly the hardest to address, is the challenge of state abstraction. And what I have here is not the actual management of state and storing that, such as in the case of a file system or relational database, but more stateful abstractions that we use as developers that behind the scene rely on a state. So here are things such as stateful orchestration and workflow management. For example, long-running transactions and Saga pattern, being able to do have schedulers and timers that kick at certain point, distributing caching, idempotency, and even abstractions that let you store and retrieve application state. So these are all developer primitives, but behind the scene, they rely on having state management. And I'm going to use this framework of 4 categories: lifecycle, networking, binding, and state abstraction, to evaluate these different projects and see what they are providing. So let's get started with Kubernetes and why it is popular in a distributed systems world, and what does it provide. First, I want to start with the foundational primitives, and the first one I would say is the health probes. So the fact that Kubernetes will do liveness checks and readiness checks on your workload and will take corrective actions when there is a problem is one of the first things that Kubernetes introduced and popularized. Now almost every runtime has out-of-the-box endpoints that allows you to do health checks, but that wasn't the case before Kubernetes. The second one I would say is around the fact that we have to measure and tell to the platform what are the resource demands of our application. And based on these declarations, the platform is able to do intelligent decisions and to do intelligent placement of our workload on the different nodes to the best suited node. That's again something that Kubernetes popularized and made part of everyday development. The next one I would say is declarative deployment, and the fact that we don't have to do any more manual upgrades of services from one version to another, and we can let the platform to do that in a controlled manner, and if something goes wrong, to roll back. And the last one I've listed here is configuration management. I think that's also important one. Before Kubernetes, we had to use some runtime libraries to look up different configurations. Now Kubernetes makes sure the right configuration is placed next to your application, available as an environment variable or as a file system for consumption. But that's not all. In addition to these foundational capabilities, Kubernetes also lets us run different kind of workloads. The easiest one, the simplest one, is the stateless, so-called 12-factor apps. And we can do that very easily with Kubernetes through replica set. But Kubernetes also lets you to manage stateful applications. For example, if you have a distributed applications and you want to manage the order in which the different instances are starting up and shutting down, and where each instance needs a certain identity and storage, etc., we can do that with a stateful set. We can also manage jobs which have to be executed until completion, periodic jobs, and even global singletons through Kubernetes. If we look at all these capabilities provided by Kubernetes, I would say that Kubernetes satisfies fully the lifecycle needs we've listed at the beginning. You can do deployments, you can do automatic placement, configuration management, resource isolation, different kind of workloads except serverless. Some might argue that Kubernetes also provides certain networking capabilities through its through its service abstraction, but I would say that is pretty limited. So it won't let us to do things such as different release strategies, to do circuit breaking, encrypting the traffic, etc. Similarly, the stateful set abstraction is not meant exactly for developer. It's a very low-level primitives. It doesn't let the developer to use a stateful abstraction straight away. So Kubernetes kind of satisfies primarily the lifecycle needs we've been talking about. And then, how can we get our other needs satisfied if that's all Kubernetes provides? And this way comes the extension mechanism in Kubernetes, and there are two. So the first one is the concept of a pod, and the pod is the Kubernetes' out of process capability composition mechanism. So it lets you transparently add other capabilities to your application. A pod gives you two sets of guarantees: deployment guarantees, that means all containers in a pod end up in the same node, and also lifecycle guarantees. So it provides certain guarantees around init containers, which have to be executed sequentially, certain guarantees around the application containers, which are running in parallel. And the concept of pod basically enables us to do the sidecar pattern. And that's the first extension mechanism used in Kubernetes. In order to explain the second concept, we first have to go quickly over how Kubernetes is working internally, and that is through the controller pattern. So the idea of the controller pattern is to run a continuous state reconciliation loop that constantly monitors the actual state of the different resources and tries to match them to the desired state. So Kubernetes have different schemas where certain resources are modeled, such as replica set and stateful set. Then for every schema, there is a controller out of the box that is responsible to match the desired state to the actual state. It turns out that the default resources in Kubernetes are not enough to model all the different needs of the different applications. That's why Kubernetes introduced the concept of custom resource definitions. And the idea of custom resource definition is that you can model you can model your own resources based on your problem domain, and that resource lives in Kubernetes next to the default or core Kubernetes resources. Once you model your problem domain, you can have an operator or custom controller that makes your desired state from the resource definition a reality. So you model your problem and you write a controller, and then you can implement your custom application. So custom resource definition and a controller makes the operator pattern, and that is the second way, I would say, to extend Kubernetes. So sidecars allow us to add orthogonal capabilities, and they are primarily used, I would say, for implementing the so-called data plane. And the operators let us to define and code some domain-specific knowledge in an executable form. And that's typically used for implementing control planes, we'll see next. Now, we've seen what Kubernetes provides out of the box and the two main extension mechanisms. I would say next, let's see some of the platforms which are built on top of Kubernetes, and they are heavily using this concept, these extension mechanisms of sidecars and operators. And let's see how this platform satisfies the needs we've listed at the beginning. The first one we're going to start with is a service mesh such as Istio. So what is it? Let's assume we have a service A and a service B, and service A tries to reach out to service B. What service mesh does is it uses the concept of sidecars, and it injects a service proxy next to each of the services. So now when service A tries to call service B, the service proxy acts as a firewall that intercepts all incoming traffic or outgoing traffic. So the call goes from service A to the service A proxy to service B proxy and to service B. And the collection of all of these service proxies are known as the data plane. The service proxies, they are light, they are stateless, and they need a mechanism to get their configuration and to report back telemetry data. This is where the control plane comes into the picture. And the collection of the data plane and control plane jointly forms what's called the service mesh architecture. It turns out we also need an API gateway to control the traffic that comes into a cluster. And you can see on the right-hand side, there is actually a good collection of different data planes, service meshes, API gateways that you can pick from. One question that comes is around the responsibilities of service mesh and API gateway. And even though it may look like at the beginning there is overlap, actually they serve different purposes. An API gateway is responsible to hide the services architecture from the consumer. So it's responsible to hide the details of your implementation. And on the other hand, a service mesh is kind of responsible for the opposite. It's responsible to give more visibility through different metrics, tracing, logging, etc., to more visibility to your services architecture. And there might be some features such as rate limiting that appear as same, but even those features serve different purposes. rate limiting in an API gateway and an API management platform is based on the business contract between the consumer and the service, whereas the rate limiting in service mesh is more driven by the technical contract of the service. So they serve different purposes, but I would say jointly, service mesh and an API gateway satisfies our networking needs we've been listing at the beginning. So service discovery, dynamic traffic routing, resiliency, security, observability, all of those are ticks. I wouldn't say service mesh does anything around binding, state management, and the lifecycle of workloads. We'll continue at the same tempo to see a few more projects. The next one I want to briefly talk about is Knative, which is a Kubernetes native platform for serverless workloads. Knative has two main components, serving and eventing. Serving is about managing request-response-driven interactions, and eventing is for event-driven interactions. Now, if I were to explain both in an example, the simplest way to define serving would be that it adds serverless characteristics to our workload. So when we create a Knative service, which is different than a Kubernetes service, different than Istio service, it basically adds serverless characteristics to our workloads, such as ability to scale to zero, ability to scale from zero up, activation, rapid auto-scaling, and also other things such as traffic shifting, splitting, and it has simplified deployment model. And all of that is for the expense of removing some, by adding some constraints, such as your workload can be only a single container with a single port, and it cannot have volumes, etc. But by using Knative service, you are basically ticking the box of the serverless workloads that we said Kubernetes doesn't have out of the box. The next concept in Knative is Knative Eventing. And to explain that, let's assume we have a service that's running on Kubernetes, and it has an endpoint that's an HTTP endpoint, and we want to connect some external system with our HTTP endpoint. What Knative Eventing gives us is it gives us all the eventing infrastructure needed for importing these external events, so connecting to an external system through source importers. For example, here you could use Apache Camel-based source importers, which lets you connect to tens or hundreds of different systems. Then Knative Eventing lets you manage those events through different broker implementations, such as Kafka or something else. And it also lets you to subscribe to these events from your service through triggers and filters. As you can see, it gives us a fully abstracted eventing infrastructure in a declarative way. If I look at the capabilities of Knative, I would say it is kind of doing a little bit of everything. It does a little bit of lifecycle management through the fact that it can do serverless workloads, so it can scale to zero and up. It does some networking through ability to do traffic shifting. It has source importers, so it has actually good capabilities around bindings to different systems. And you would say that through the brokers and backed by Kafka, it also does some state management. It doesn't satisfy all the needs we've been talking about, but it touches all the areas. The last project that I'm going to look very briefly is Dapr. It's a project started by Microsoft less than a year, and I would describe it as a portable runtime, with the distributed primitives in a sidecar. So it's a sidecar with a set of capabilities. The difference to, let's say, to service mesh and Envoy, the service proxy, is that Dapr is not a transparent sidecar. So it's a very explicit sidecar that your application has to call in order to make it do something. And your application can reach out to the sidecar over HTTP or gRPC. These are the two main protocols, and you can run it, on a VM or Kubernetes. Inside the sidecar, there are a set of capabilities, and these capabilities are called building blocks. And a building block is nothing more than an API. So it's an HTTP or gRPC API with a swappable and pluggable implementation. For example, there is a state management building block. So there is a state management API that you can do operations such as put and get. So you can store, state, and get. And behind the scene, you can choose what implementation you want to use. It can be Cassandra or Redis or SQL Server or some kind of a cloud service. Similarly, it has publish subscribe API, which lets your application to send pub-sub messages to other applications. And that pub-sub capability API can be backed by Kafka or some kind of cloud service. Then it has a good set of resource bindings, so adapters that can poll external systems, or they can send events to these external systems, and a few others, things such as service-to-service invocation. The very recent one is the ability to look up secrets, actors, observability, etc. If you look at the architecture, your application at the top can use a client SDK, but it can also just use the capabilities of the runtime. If it's Java or Python, in any of these programming languages listed here, you can do an HTTP call and interact with Dapr. Deployed on Kubernetes, it is using the concepts we've been describing. So it is relying on sidecars. So there is a Dapr sidecar injected in the pod with your application. Then there is a Dapr operator, which is responsible to configure your sidecar and interact with the external system. There is a sidecar injector, certificate issuer, entry, and actors placement. But overall, we can say that it is heavily using the sidecar and the operator approach. If I look at the capabilities of Dapr, first, it's not doing anything around the lifecycle aspect. The sidecar is sitting next to your application, and you have to interact with it. It definitely has some capabilities around networking through service-to-service interaction, pub-sub, or even things such as retry, circuit breaking, etc. It has a good selection of bindings, good selection of connectors, and it also attempts to do some stateful abstractions through its key value store lookups and storage. So it ticks few of the box, I would say. Now, this list goes on. We are not going to look at all these projects, but just to list a few which are again similar. Cloud State by Lightbend is providing stateful abstractions for serverless applications. It's again using sidecars. Rather than HTTP, it offers only gRPC. But you as a developer, you get out-of-the-box primitives, for example, for things such as a pub-sub, key values store, event sourcing, CQRS, etc. It's again the sidecar model. Scupper by Red Hat is a project that lets you connect applications cross clusters and even cross clouds. The difference here is that Scupper is not a sidecar per application, but it's a shared sidecar. So you would have a sidecar, say, in a namespace that multiple services can use to interact with some other cluster. And Apache Camel and its subproject Camel K are also using operator. In this case, Camel K operator is attempting to drastically improve the developer experience with sub-second deployment of camel routes into a Kubernetes cluster. In this case, Camel K is not a sidecar, but still an interesting model with an operator. And I would say there are more sidecars, log collection sidecars, proxies for authentication, caching, etc. Now, what we can take from this review so far is that I would say operators and sidecars are gaining popularity. That's one. And probably the second one is that there is no single sidecar or a project that's going to rule them all. They all provide certain capabilities, but lack in some other areas. So let's try to maybe predict how future architectures, sidecars might look like. Now, I've created here an opinionated list of few of the interesting developments I observe in each of these categories. I'll go quickly over those. As we see in the lifecycle management is primarily handled by Kubernetes, and Kubernetes API is now very stable. It's not going to change its core part, but there is a chance that we may get some better sidecars. Now, the issue 753, which may or may not be accepted in upstream Kubernetes. Anyway, there is a proposal to make basically sidecars more explicit. What that means is if that issue is accepted or something similar is implemented, you can mark a container as a sidecar, and that container will start before the other application containers. So when your application starts up, it can rely that there is let's say, an Envoy sidecar up and running, and I can talk outside during startup. The other trend I would say is on the lifecycle side is around operators. Probably we'll see more operators and better operators, and we can see that already on Operator Hub. And whenever the Kubernetes API is not good enough to manage the lifecycle of your application or the day two concerns, operators can help. For example, if you want to deploy a more complex application and the deployment model in Kubernetes is not good enough, you can implement logic in your operator. If the health check through liveness check and readiness check is not good enough, you can implement health checks in your operator. You can implement backupping to S3 and ability to restore of your application. You can implement things such as automatically creating alerts and dashboards when your application is installed. And that list goes on and on. And I would say probably operators will be a way to innovate around the lifecycle management of applications. On the networking side, an interesting project is Data Plane Development Kit, which is a quite low-level project. It works at the operating system level, but it provides libraries that will accelerate packet processing between the containers in a pod. So we can expect that sidecars will incur lower overhead when they do networking connections. Another interesting thing is around latest developments with Envoy. They are adding more and more protocols, layer 7 protocols, such as Kafka, the very recent one, and they added WebAssembly support. So we can expect that there will be interesting experiment and interesting primitives running in an Envoy sidecar soon. If we jump to bindings, I would say the main tendency here is that we see the bindings are moving outside of your application. So all these connectors, if you look into Knative and even Dapr, they run as a separate runtime. So you as an application developer, you don't have to worry about the actual connections, different connectors, protocols within external systems. A separate runtime can connect there and pass those events to your application over HTTP. And on state, I would say probably more work is needed there. Currently, there is not there are a few early attempts to provide stateful abstractions, but there are not polyglot ways to use stateful abstractions to do things such as data federation, change data capture, caching, idempotency. You cannot just declare a sidecar with these capabilities and use it. Now, if those predictions come true and developments go forward, so how would a service, microservice might look like in the future? I would say even right now. So when you create a service, you use certain capabilities from the platform, from Kubernetes. Yeah, that's a fact. Then on top of that, probably you will use one or more sidecars. Maybe you'll use Envoy, and you may use Knative next to that, or you may use some specialized sidecar that does enterprise integration patterns or just stateful abstractions. And on top of that, you would write your business logic in your preferred language. So what I think might happen is we may have some application-centric APIs, the red box there. What I mean by that is in order to consume these different primitives from certain sidecars, we may have APIs that defines how to do pub/sub, storage, EIPs, etc. over HTTP and gRPC, something like Dapr is attempting to do right now. That's one thing. And if we look at the whole stack, I would say the service is a so-called multi-runtime service, because you have your polyglot business logic. Next to that, you have a few sidecars, and the whole thing is your service. And software developer vendors, in addition to providing these sidecars and certain capabilities, they are also now providing an operator, basically the ops included mentality, where the operator knows what's the best way to manage your containerized workloads. And most of the projects we've seen so far, they also provide something like a CLI and IDE plugins that are allowing you to develop locally and also to deploy fast to a Kubernetes platform and even configure things such as sidecars and your application runtime. So if we go back, we said we want to write some business logic, and we need certain set of distributed primitives. I would say you will be probably writing your business logic in a higher level language. Maybe that's Java, .NET, Python, doesn't matter. That business logic is always custom. That's your runtime, and you will consume the distributed primitives around networking, binding, state management, and even lifecycle from the platform or through some kind of sidecars. And you configure your sidecar declaratively, with a bunch of YAML files, and together your business logic and a bunch of sidecars represent your multi-runtime service. And that brings us to the question we had at the beginning: what comes after microservices? If we look at how application architectures have been evolving. We started with a monolithic architecture such as ESBs, where we had to put together business logic with some on the platform where it already had these primitives. Then with microservices, it allowed us to split our business logic into independent applications. So we split them vertically, I would say. And each microservice would have its set of distributed primitives. Now, what happens with serverless and function model is that for certain microservices which are composed of, let's say, single operation and have more dynamic nature that requires rapid scaling up and scaling to zero, you can use, and it makes sense to use serverless and functions. But for some other microservices which are reasonable complexity, probably what we will see is this kind of horizontal split where you have your business logic developed in-house and you accompany that with a sidecar, one or more, that you get the distributed primitives next to it, and you deploy both of them or multiple of those together, and that's so-called, I would say, multi-runtime microservices that might come. With that, I want to give you this link where you can get a copy of our book and my Twitter handle where we can continue this discussion.
Yeah. All right. So thank you so much for that. That was awesome. And I do love this content because a lot more people should be thinking about Kubernetes more abstractly, right? And that's the nature of patterns, right? And abstraction around different aspects of it. And what's cool about it from a DevNation standpoint, we've done sessions on Istio. We've done sessions on CamelK, Scupper. I made some notes and put links into the chat for people who are looking at these technologies. So Knative, right, Tecton, a lot of the things you mentioned briefly and touched on, sidecars. We saw a lot of sidecars in our DevNation Master courses and in previous DevNation Tech Talks. So at this point, we are out of time. So unfortunately, we won't have time for any questions. But I thank you so much for what you did. That it was a great presentation. The recording will be available. The slides will also be available on the URL that you guys hopefully are looking at right now on the developers.reddit.com website. If not, you will get an email from us that will basically tell you where those slides are and then where the recording is. And of course, you can follow us and like us on YouTube, and that'll get you notified for more future tech talks as they come out. So Bilgin, thank you so much for your time. It was absolutely fantastic.
Thanks for having me. Bye.
All right, and at this point, I got to stop this stream and then get ready for another one. So we'll see you guys in a few more minutes with a whole different topic. Thank you, Bilgin. We're out of here.